So can anyone, is everyone hear me clearly? If I don't use the mic, so everyone can hear me clearly. Okay, no problem. Then probably I don't use the mic because I like to walk here, walk there during the presentation. Then I myself also feel free a bit. Okay? It's not that sharp. Can we make it the screen sharper a bit? Whether it is adjustable. Yes. So if we can adjust the okay? Can see the screen clearly? Okay, good. Maybe for the students here, maybe you can turn a little bit so that the face. Okay, thank you. Okay, so good morning everyone. Semua sudah makan sarapan pagi? Very good. So you should have more energy than me. Okay. Okay. So everyone ready? So my name is Chan. You can call me Jim Boon, just like Dr. Chan call me usually. And I have been working in the construction industry, including my first year experience as a consultant. The whole career of mine is about 11 years. I graduated USM in Penang. So I'm civil engineering background. And I believe all of us here the same. And today we're going to talk about the geogrid application, which is where most of my career I've been training under this geogrid application. And then I will share with you some of the case history using the geogrid in Malaysia. Okay? So, have you heard about geogrid?
Never.
Never. So nobody knows about geogrid, right? Anyone? No. Okay, so just now my colleague has actually passed over some of the brochures. You can open it up, and then inside there are some samples. That are the material of, we call geogrid. Okay, but in fact when we talk about geogrid, there are some other type of geogrid. So this is only some of them, which is a product of mine actually, that we carry as a distributor in Malaysia. But today I'm not going to talk about the commercial part. I will share more on the technical knowledge. Okay. Next. So this is basically the services and the experience that my company has. You can see two logos over here. One is the product that you have over there, which we call Hansa. It's a manufacturer, one of the manufacturers of geogrid. And the other one, you can see these logos here. MEGAS is where I come from. Okay, so my company is MEGAS Solutions, Sendirian Berhad. In short, you can call us MEGAS. So basically, the service and experience that we have, including the pavement optimization using geogrid. Okay, you can see the triangular shape one, which is those type of geogrid. And reinforce of the steep slope, we're quite active in the repair of the landslide using this reinforced system as well. Then there are some ground stabilization improvement, including some retaining wall structures, which we call it as a tensile system retaining wall. Okay, next. So in today's sharing, I will talk about basically about two parts. One part is the use of the geogrid in road construction and the subgrade stabilization, which is using the triangular type of material, that geogrid. The other one is talking about the geogrid reinforced soil system. Basically, it's a vertical structure like reinforced slope, retaining wall, using the we call a uniaxial geogrid, the one in the strip one. Okay. Then I will share with you some of the case history in Malaysia using this geogrid. Next. So first, we will talk about the use of the geogrid in the road construction and the stabilization. Next. So basically, there are 6 application areas that we can use the geogrid for ground stabilization. One is to reduce the layer thickness. We understand that if we design for a pavement, for example, okay, if we need a heavier load to support the heavier load on top, for example, that road we know that most of the time lorry is using, we call heavy duty road, then in the unbound layer, we might need to put a very thick kasharan layer, for example. So in order to optimize it in terms of cost, in terms of construction time, we can reduce the thickness, the layer thickness, by giving you the same performance of the pavement by using the stabilization geogrid. Next. So another one is, let's say, we have money, we have budget to do the pavement. But what I don't want is that I don't want it to maintain it frequently or very often. Can you extend the life of the pavement? Yes. We can put the geogrid in so that we can increase the life of the pavement, because all the pavement that we design for, there's a life. Whether it's designed for 5 years, whether it's designed for 10 years, okay? So, for example, if a client requests, no, I don't want 10 years, I want 20 years, can it be done? Yeah, it can be done. So if we maintain the thickness by putting a layer of the geogrid, probably we can extend it. The original design here is talking about 10 years life. By having a layer or multi-layers of the geogrid, we can increase the life to maybe 15 years to 20 years for the same type of performance. So increase the bearing capacity. By using the stabilization geogrid, we incorporate into the granular layer, which is something like kasharan. You understand what is kasharan, right? Okay, very good. So, for example, the kasharan, then we are able to increase the bearing capacity. So how we do that is actually through the increase the stiffness. Once we increase the stiffness by, later I'll explain the interlocking of this one to the kasharan layer. So once we increase the stiffness, we are able to widen the load spread angle. So once we widen the load spreading angle, meaning that if we have same loading, for example, if the load spreading angle become wider, meaning that the A is bigger, we understand that the stress is what formula? What is the formula for stress? This table first. You? Huh? Force per area. You? Anyone? Agree with us?
Yeah, force per area.
Okay, very good. Yes, it's force per area. So if we are actually, if say we are able to increase the load spreading angle, we have a bigger A subject to the same F. So what will be the stress? Smaller. Because A is bigger, F is maintained, the stress will be smaller. So that is in the sense that we are actually able to increase the bearing capacity, because we are able to increase, if let's say the same stress, then meaning that we can apply more F, more force onto the thing, apply on the widened area. So that is how we can increase the bearing capacity. Okay? Okay, can follow? Okay, next. This is to control the differential settlement. When we talk about settlement, basically we understand 2 types of settlement. One is the total settlement, the other one is the differential settlement. So total settlement is that the whole thing, if let's say we put a platform and the whole thing settled together without any differential settlement in between, that's we call total settlement, is settled together. Okay? Total settlement means that if I have one platform at the left hand side, one platform at the right hand side, the settlement rate between them is different. This one, right hand side settle faster, this one slower. So over the time, you will have the differential settlement. So by using the stabilization geogrid, we are able to control the differential settlement. Not to say that once I put that, there's no settlement at all. But instead of sudden drop of this type of differential settlement, it will smoothen out the differential settlement. From here to here. Okay? This is very useful when we use it for like some of the projects like road widening. If you do observe that, for example, Pago now is having quite a good development. You will see that some of the road where the government or JTI are actually doing the widening on the left hand side, for example. You can try to observe maybe after 3 months, after 6 months. maybe it will happen in between the transition between the old pavement and the new pavement. There's a differential settlement. You can always observe that. Maybe next time you put some attention onto it. When you see they do the widening, then you keep in mind 3 months later, 6 months later, you have a look. It always will happen, the differential settlement. The reason is, once they open up this one, it's subject to the traffic load. Then the consolidation rate at the widening portion, it become faster. So always this part, we have the differential settlement on at the transition of the new pavement and the old pavement. Okay? Next. Capping the weak deposit. This is most of the time, sometimes we create, for example, a construction access road. So construction machinery normally is quite heavy, okay? And then some of the site maybe due to some weak deposit or maybe high water level or whatsoever. When the construction vehicle is trying to access in, then it will have the bunching failure, it will cause an overturn of the machinery, this and that. This is very useful for capping the weak deposit so that you won't have the bunching failure problem due to the heavy load of the construction machineries. Next. So another one is spanning over the voids. So if you see this void is something like sinkhole. Do you understand what is sinkhole? Okay, very good. So this one is not to say that it can eliminate the problem of the sinkhole, but it can span over the void so that it gives us some sign before the things collapse. Okay, it can extend a little bit that this problem happened, so that it gives us some sign that if there's something wrong on the road here, why it becomes a sudden collapse with some settlement, all this. Then probably the maintenance people, they can take some action and then excavate out and notice that, oh, there's a sinkhole at below already. Without this one, probably it will collapse in sudden. Okay, so you will have this type of function as well. So the history of the geosynthetics in road is concerned. So first of all, I would like to explain geosynthetic. Geosynthetic actually is the group name, I would say. And then below that, we have geotextile, we have geogrid, we have some membrane or clay liner membrane or whatsoever. So problems always occur at road. Like I say, this is having the weak deposit problem. And then when the heavy machinery go through, if you create this type of rutting, or maybe it causes overturning. Okay? So the solution, where people trying to use it all over the years is concerned, they're trying to use a woven geotextile to actually stabilize this access road. Woven geogrid, welded geogrid, punch and drawn geogrids. So what are the difference in between all these materials? I will circulate this for you. Maybe I'll start from this table for some material here. Then you can feel the difference of this material. This is the stabilization geogrid, which you also have it with you on the table, which is a triaxial geogrid called triangular shape. This one also acts as a stabilization geogrid, but it's in, we call it biaxial geogrid. Okay, later I will explain the difference a little bit. And this is the uniaxial geogrid. This is not really for this road stabilization or stabilization purpose. This is more for the reinforcement on the vertical structure. Okay. And this is the polyester type of woven. This is woven geotextile, and this is non-woven geotextile. This to give you strength. This is to put it as a separation only. Okay. I will circulate around the. But please, after the session, return it to me. Okay. Okay, next. So what are the differences in terms of performance? Later we'll discuss about it. And what are the features of this geogrid that influence the performance? Next. Okay. In road is concerned a bit different from the structure is that in road, we have a road over here. Always the loading is perpendicular to the road. Okay? So if let's say we put a reinforced type of material, For example, those woven geotextile, those reinforcement onto the road stabilization is concerned, then how it can behave. We understand all these geosynthetic material with the high tensile strength, and how it achieve their tensile strength is concerned. It has to elongate. It has to elongate. If you study some of the, if you have chance to study some of the specification sheet of the tensile strength type of material, you will understand that you need to achieve certain strain to achieve the tensile strength. I will explain, I will illustrate it later. So unlike the vertical structure, like for example all those retaining structure, the loading is always perpendicular to the reinforcement. This one, if you put the reinforcement or the stabilization, the loading is perpendicular to the road. Okay? Thanks. So, for example, if this one is representing the geogrid or the geosynthetic material that we put under the road, and this boy is representing a tire of the vehicle. So when we apply from here and to here, what you can see, this one actually it starts to elongate, so that it mobilizes the forces, it mobilizes the tensile strength to support the weight of this boy. Okay. So if we put this scenario onto a road, for example, we have a road here, and then with the weak subgrade, for example, and then we put some geosynthetic material over here, and then the wheels start to go through. For the geosynthetic material inside the road to mobilize the forces, what will happen? Yes, settlement. You will start to settle, you will start to have some this type of problem before it achieves the full strength to support the load on top. Okay? So in this scenario is concerned, we call tension membrane mechanism. Yes, the tension is based on the tension on its performance. Next. So this is the tension membrane which I explained to you. This is the PP woven geotextile. Similar way of acting on it. It needs to have elongation. It needs to have settlement so that it can achieve the strength to support the loading. While you can see that if we use a stabilization tubing, where you can see those type of stiff tubing. This type of stiff tubing, even you hold it this way, and compare to the maybe geotextile or material that you hold it this way. This one you can see that it can't hold by itself. This one can hold by itself, this one cannot hold by itself. So this tells you that on the material itself, this is a stiffer material, this is a less stiffer material. But in terms of tensile strength, it's different. This one is good, this one is not good. But from these pictures, you can see that in terms of stabilization supporting the load, which one is better? Because now we are not talking about a retaining structure where the load actually is perpendicular to the reinforcement. Now we are talking about the load is perpendicular to the reinforcement. Okay? Next. So in this video is concerned, later I'll play a video for a short while on this part. So you can see that this group of people actually is taking the woven geotextile, is trying to stabilize the base here before they do the backfilling on this swampy area. So they are trying to walk into the site and do the installation. You see how difficult they can do the installation. Even when they unroll it, they try to step on it, but they still sink. This is just now I demonstrate to you the hammock one. When there's a rope on top, it has to sink until it mobilizes the strength to support. So, but you see, when they during the installation of those stiff geogrid, when they unroll it, it can start support people on top of it without any granular material being installed, just like in this case. And of course, now actually both in roll, so actually this is okay. So you get some. So in this slide, I try to explain again the difference between the tension membrane effect and the interlocking mechanism. This is where your synthetic material or your high strength or textile or whatsoever, where you have a very good strength. But this strength you have to achieve with the elongation. That's why we call it tension membrane. And at the same time, it requires anchorage at the both sides extra long so that it can have something to hold at the left and right. Okay? And this one, actually it has a minimum strength, but it's a very stiff jewelry. It does not require the anchorage length. So you just need to, for example, if your rope is about 3 meters, then you just place 3 meters. You don't need to have extra another 1 meter, for example, at the left, and extra another 1 meter at the right. Okay. So in the road construction or access road or working platform or whatsoever, what is the key performance indicator? It's actually deformation. If today we do a road, whichever engineering method that we apply, as long as it doesn't deform or it doesn't settle, then you consider this design is successful. Agree? Okay. So when talk about deformation is concerned, or in engineering term we call rutting is concerned, what are the causes causing the rutting? Number one, if you look at this diagram, there's a wheel load over here applying onto the, I will use as a road, apply on the road. When this load is trying to apply, it's trying to push all these aggregate, some of the aggregate try to push it, so it keep up at the side here. Some it will actually squeeze so that it move left and right laterally, and then maybe the bottom one, some it will sink into the existing subgrade. Then some of the subgrade material will go into it. This one we call the inter-penetration. Okay? So the whole process of this, it will cause the rutting created by the wheel load. Okay? So you understand what is rutting? Sorry? Yeah. Don't understand what is rutting? Rutting, actually, it is a settlement of the road. So you can see that the wheel path, it has this type of settlement. But the measurement of the rutting and deformation is different. Because like I say that when there's a wheel load applied on top of this road, it will try to squeeze so that over here you will have a little bit up here. Here we have a little bit up here. And then you feel that there's a settlement on the road. Okay? So the rutting measurement will start to measure from this up here to the base here, where deformation is from the original level and to the base here. Okay. So when the road starts to have rutting, if you are the driver, then you don't feel comfortable. For example, your wheel is here, then you drive. When you drop here, you feel there's a drop. Okay. So always there's a requirement on the road design is concerned. For example, it's something like 40 mm. If normal road, if it's for the heavy duty pavement, maybe they are up slightly more. Okay, that is to give us the comfortability when using the road. Okay. Next. This one I've explained earlier. So basically, these are the notes talking about the stabilization jewelry using the interlocking mechanism, and those are geotextile or reinforcement jewelry using the tension membrane mechanism. So interlocking, why this one? When you use it for the stabilization, it will be more successful than the tension membrane mechanism. The reason is, like I say, this is a stiff jewelry, okay? And when we start to compact the kasharan on top of this layer, the kasharan, the stone, will actually lock by this grip. So once you lock already, this one, it won't move. And it start to form the interlocking on top of it. Okay? So just try to imagine. I think some of you may have played the snooker before. Okay? So when we play the snooker, we arrange the ball in the triangular rack, I would say, triangular rack. Then you try to place the ball won't move. So if next time when you go to the game again, probably you can stack up the ball and form a pyramid with the rack. Okay? It will form the pyramid. So why it can form the pyramid on top of it? Because the bottom one is confined, the bottom ball, the ball at the bottom is confined by the triangular rack, where the top one is interlocked to each other because the bottom don't move. Okay? The balls at the bottom don't move. So you can apply a small load on top of it, it won't collapse, the pyramid will still remain. But if you take up the whole thing will spread. So the similar concept on this one is called the interlocking, so that we use that concept over here. You have to interlock the stone all together. So when there's a load applied on top of it, you will have a very good confinement to prevent the stone move sideways. Remember just now the causes of rutting that slide? You will prevent the stone from moving sideways to prevent it settle down as well. So there are still some in the industry, they use a tension membrane mechanism as a design to stabilize the rope. They still can do it. I mean, all these are engineering methods, they still can do it, but probably in the constructions method, they have to emphasize some of the method. I explained to you, this is one of the methods that if they use tension membrane jewelry or reinforcement to stabilize the rope. So this red color one is representing the geosynthetic material with the strength, and they start placing those granular material. So they use a lorry to move up and down during the construction so that they can create this one to achieve the required strength. Okay, so this one is under tension, they achieve the strength to support this lorry load good enough. So the same one applied to the center part. Next. Okay, when they do it all over the section of the embankment of the road, and then they start to fill up. Next. And then construct the road. But the problem here is, when you finish the road, whether the lorry or the vehicles will always follow on this wheel path or not. They will not. Maybe next. This is where the wheel path is, but over here there's no tension process being done. And also, by creating all this, actually we're creating a pocket to actually keep water. Then we have problem of all this subject later on. Next. Then when it comes to the time that we need to do maintenance, we need to dig down, probably to install some subsoil drain or whatsoever. We have to cut away all this jewelry. Once you cut away, then the effect of this jewelry of this membrane jewelry over here, gone. No more effect anymore. Remember I said that tension membrane mechanism, we need anchorage length. So by cutting this away, this part, no anchorage length on this one. This one totally no anchorage length at all. So this one is become useless. Next. When using this stabilization jewelry, whether the same problem will occur or not, especially during the maintenance part. So this one, as I say, it doesn't require anchorage because the stabilization is very on the interlocking, so it's the immediate effect that they give you. We don't need to get the lorries or whatsoever, try to tension it, apply the work to tension it. Okay? Next. So if when come to, how about when I need to do the maintenance? Can I cut this jewelry? Yes, you can do it. So for example, next. If this is the part that you need to do the maintenance, for example, this is the part that you need to install the services over here. Then, during the excavation, we probably need to allow a little bit more on 4 sides. Okay? And then we excavate down. Next. Excavate down. Next. Then we cut the jewelry away. Okay? Cut the jewelry away for the area where we require. So there are still 200 extra here, 200 extra here, for example. Okay? Next. And then we dig down furthermore, that is the part that we need to do the installation of the services. So after we get it done, next, we can just cut another new piece of this jewelry and then put it back with a simple overlapping over here, which is 200 mm. Then you backfill with the granular material and do everything up. This one will give you the same performance as its original. So in terms of maintenance, it will be easier because this one we don't need to have the anchorage length, number one. Number two, we don't need to have those tension forces to apply. So this is some of the real trafficking tests that they use the real machine and then put in the jewelry to demonstrate the real condition of the pavement. So CBR basically is about 2% of the something. So you can see that there are 3 sections being done. One part is called control section, meaning that there's nothing put inside it without any geosynthetic. There's nothing, just the original with the granular material. So after 2,000 passes, it has a problem with it. Very big butting over here, you can see. And in fact, over here, it should have one more line. I'm not sure why it's not. This is representing the subgrid. Okay? You will have the same similar pattern over here with the settlement after 2,000 passes, with a deformation of about close to about 100 mm. Okay? Then when you look at the use another type of welded grid, which is the tension membrane type of geogrid, it improved condition. After 9,000 passes, the heat on the surface hit about 100 mm as well. After 9,000 passes, then we have a failure. And there's a deformation on the subgrade level as well. So this one is using the stabilization geogrid. SS30 actually is one type of the biaxial geogrid, the one I circulated now. When you finish looking over there, you can change to here, then this one change to the other side, so your friend also can see. So this one is you can see that after 10,000 passes, the rutting is still quite minimum, which is about 40 mm. Okay? And almost there's no effect on the subgrade degrees. Not really see the effect. So if you plot all the result into the graph, this is a control section. After 2,000 passes, it's 140 mm. This is using the tension membrane. If you look at this line, which is at 6,000 passes, the pavement using the tension membrane geogrid achieved close to 100 mm, where this one is about 45, 50 over mm. So it improved the performance from here to here is quite a lot, easily about 2 times. This one to this one, easily about 1 time. This is where I explained just now for the interlocking. So this is how it works. So one of the very important features that to form the interlocking mechanism on the geogrid is concerned is the rib profile. Okay? So rib profile is concerned if you look at this grid and this grid. Okay? You can have a feel to this. This is actually very flat type of, it's almost flat. And this one, if you look at the rib is actually this one we call rib. There's a thickness on the rib. Why the thickness is important, we can see on the following slides. Next. This is a flat type of rib profile. It's quite flat. It's something like this. So it's like, okay. So you can see just now in the slide, you can see the stone actually, when there's a load applied, the stone can actually grow from one rib to another rib because this one is quite flat. Next. So these are grid, there's a thickness, is quite thick on the rib as compared to the flat one. So when there's a load applied, it will actually hold. And this is how the confinement and the interlocking can be formed by using this type of stabilization. And another important feature is that this dot over here, we call it junction. The junction must be as stiff as possible, meaning that it cannot move. If the junction is able to move here, then the stone is able to move. When the stone is able to move, the whole layer of the stone, it will lose. And it lose, it lost the stiffness. When it lost the stiffness, then it reduces the capability to support the load on top. This is how it is locked. The bottom one is locked by this. So the stone at the bottom is locked by the grid. The top one is interlocked by the stone. Okay? Next. This is talking about the efficiency of the junction efficiency. Next. So always we are looking at the junction efficiency of this grid is almost 100% to this rate, the stiffness, in terms of stiffness. So it's not able to. in this diagram is concerned, always there is an effective confinement zone or interlocking zone for one layer of the grid. We would always recommend that you need a minimum of 150 mm to form the interlocking. Too little cannot. Okay? And then if it's very thick, more than 400 mm, we will recommend another layer of this interlocking jewelry to be placed. Okay? So meaning that for one layer, the thickness is from 150 mm to 400 mm. If in the design, for example, if let's say we design for the hot access road or heavy duty pavement, probably we need to use a multi-layer because the layer that we need is much thicker. For example, 600 mm or 800 mm, depends on the life, on the load that we design for. Okay? Thanks. Okay. The good thing of this, triaxial geogrid is that from the research, we can actually study and see how the load distribution of this geogrid. So the good thing of this is actually, this is a multi-directional geogrid. Why multi-directional is important? For example, if we use it for the road, then probably those type of biaxial geogrid. This is a biaxial geogrid. We have the X and Y direction only. So if we use it for the normal pavement road, for example, the road outside, normally the car will actually go this way, or the car will go this way. So biaxial maybe is okay already. But in terms of load distribution, this is still not perfect. Okay? So to make it much better in terms of load distribution, for example, if you want to use it for the car park, or we use it for the some working platform on those fabrication factory, because car park is concerned, sometimes the car can go this way, this way, this way, this way, anyway. Then for the working platform in some of the fabrication yard is concerned, the machinery can be go anyway. So the research and the invention of this triaxial geogrid is actually to take care of that part so that we make the load distribution more complete and more efficient onto the ground. When it's more efficient is concerned, then we're talking about multi-directional. Okay? So the load distribution of this triaxial geogrid actually is not this triangle, the hexagon. So this hexagon is almost a circle, almost like a circle. If we apply on a load, the best of the load can distribute onto the ground actually is by the circular. So it's complete all angle. This is not 100% yet, but it's quite close. Later I will show some research result on the stiffness of this multi-directional geogrid. Next. At least we talk about multi-directional. So in this diagram is concerned, they actually run some trafficking tests on the. They actually run some trafficking tests on the biaxial geogrid to see what is the performance on the main direction, then main direction plus 45 degrees, and then the main direction plus 90 degrees. Okay. So you can see that over here it has 160 passes, where the deformation is 25 mm. Okay, next. So when they do, in this cross direction, which is about 45 degrees on the machine direction, you can see that the performance to achieve the same settlement or deformation is dropped from 160 passes to 37 passes. At this direction, I run my vehicle 160 passes, it has 35 mm deformation. When I do it in this direction, 45 degrees to the machine direction, after 37 passes, is already achieved 35 mm deformation. So next. So the same test, we run it on this multi-directional geogrid to look at how it's performed. We run it to the machine direction. After 132 passes, we achieve 25 mm deformation. Next. We run it 45 degrees to the machine direction of the geogrid. After 176 passes, we achieve 25. So obviously you can see that this one, as compared to the biaxial as we compared earlier, it improved from 30 over passes to 170 76 passes. Okay, so this is to show that the importance of the grid in this manner to perform in the multi-direction purposes. So when we put all the radial stiffness onto this chart and then start to plot, this is the one machine direction. It has a better stiffness, which when the number of passes over the settlement is more, then the stiffness over the deformation is better. So it has a higher radial stiffness. So this is 45 degree, and this is again the 90 degree. Then you plot it to every angle, then you get the graph of something like a star like that. Then when we plot the same onto this triaxial geometry, then you can see that it's almost circular in terms of its stiffness in different angles. So the radial stiffness ratio for this point and this point is about 0.3, so there's a difference. And the radial stiffness from this point and this point, or maybe this point, if you look at it is concerned, is about 0.75 to 0.8. So when close to 1 meaning that is a perfect circle. Okay, so this is almost there. So this is the same thing. Let's explain this now. So at the same time, they also record some of the result from the test to check how you can improve the life from biaxial to triaxial. So you can see over here is concerned, this part is talking about the deformation of the pavement, and this one is to record the number of passes. So the control means that, again, there's nothing. It's original, just a stone layer itself, and then with the subgrade. Subgrade condition is the same. And we put a layer of biaxial geometry, and we put a layer on the triaxial geometry at the different section. And then you can see, after they plot out the result, let's say we take 6,000 passes to compare. At 6,000 passes, the triax, the test run with the triax record less than 30 mm. Sorry, it's 20 mm. And then with the biax, it's almost about 30 mm. So you can see the improve even with the triax as well. Okay. So of course, we have some in-house program to actually study what is where we need to design the pavement we call a tensile pavement. Then we can put all the materials, all the information of the pavement into the software, and then run, and then we compare. This part is to show that the pavement section without any stabilization to achieve a 5 million ISO. So this part is to show that if let's say I incorporate one layer of the stabilization unit, how much I can reduce on this root base layer. Okay. So always we have to remember that by reducing this one, we are not only saving the cost for the root base material, we are also saving the construction time, we are also saving the excavation. So with all this together, then we optimize the design as well as the construction part. So we reduce the cost. So this is a summary between the mechanical stabilization based on the interlocking mechanism. Then this is a summary on the tension and grade. So actually all this we actually discussed just now. Okay. So this is a video to show you that in this is an existing subgrade, and we have a very heavy lorry loaded with the sand, which is up to about, I can't see the, I'm not sure. Okay, subgrade CBR is quite small, it's quite low, which is about 0.5. So the truck load fully loaded is about 55 tons. This truck. So this is actually a oil sand mine project in Canada. So what they do is that they create this access road for this big boy to run on top of it. They put in 300 mm thick of the stone material, granular material. This layer, when you see, is with a layer of TX160, which is this triaxial jogging, with a layer. Then subsequent, and this part is concerned, is without reinforcement, without the stabilization jogging, but with the same thickness of the aggregate. We see what is the difference. Perfectly okay, it runs smoothly. If you stand at the side here, you can feel the vibration. This is when the truck goes into the section where there's no stabilization. We have big rutting, it mix all the stone and the subgrade material together. Once it mixed together, then the property of this imported material will change. It becomes a lousy material. So the problem will become worse and worse. Okay? So this is just that you have a view. Next. So when we consider the stabilization jogging, of course, range of the application, there are 6 applications we can apply at the quite early slide. Then if we look for this sustainable construction, okay. If you need cost saving, of course, everyone wants something cheap, something without GST. Okay, all right. Next. Longer design life. Some clients, they might prefer this one rather than this one. They don't mind to spend more money at the beginning stage, then they reduce the maintenance and then reduce the headache on the maintenance. So maybe they prefer longer design life. A long-term value, similar to all this. When you apply to all these, you have less maintenance problem, it gives you a better performance, it reduces your material, for example, imported material to be used on site. So all this, it gives you a long-term value. Okay. So these are the few factors that we can consider using this kind of stabilization. Next. So we'll look at some of the case history today. Basically, I will show we use some roadway stabilization on paved and unpaved road, then some working platform stabilization. So this is a project in Selangor, we call Selangor Science Park 2, where I believe some of you may have heard of University Multimedia Malaysia, MMU. Yeah, it's in Cyberjaya. So this is Cyberjaya, and this site is very near to Cyberjaya. This is the Elite Highway. So the site we're talking about is over here. Okay, so this is a very virgin, after the site clearing, the very virgin view of the site. You can see that a mix of the pit soil, some with a low CPR is less than 4 and very high water table is wet everywhere. Okay. So, in order to convince the client and the consultant, we decided to run some trial. So we take 2 parts of the road, one part over here we call section A, the other part over here we call section B, and then do some trial to compare the performance with geogrid, without geogrid, paved, unpaved. Okay. So section A is concerned, we call it missing link, which provides link between the Science Park 2 and Cyberjaya. Section B is a road 4, and it was expected there are some container trucks to be used in the transport. So both section A and section B has a PT ground, because of the ground condition. Varies from about 7 meters to 10.5 meters. The top 2 meters actually will remove so that you prepare a better platform during the construction. So this is a traffic study by the consultant. From here, they do the estimation on the traffic in 20 years. So this is the calculation for 20 years life and 10 years life. So we base on all this data, we come up the design, we put into the program. So this is a photo to show that the beginning of the construction of the trial section. There's a layer of non-woven geotextile. You can see the white color geotextile. As a separator between the subgrade and the subbase or the sand area. And then after the sand layer, we put the stabilization yogurt, then kasharat, which is the road base. Okay. So section A is concerned, it's all without any geometric material. The difference is there are two parts. We divide into two parts. One part is that with the pavement, which is outspart by the other one is unpaved. Okay, 450 mm thick of the road base, 100 mm of the surface, which is a sand layer. So section B is concerned with geogrid, but without pavement, without the crossing. So we put on the truck, the 3-axle truck loaded up to about 37 tons, and then keep running to look at the performance of all this thing. And then we measure the rutting, which is the rut depth, after completed 120 passes, which is by calculating equivalent to 4,004 inches. And then we put on a ruler and then start measure. So on section A is concerned, this is totally without any stabilization geogrid. Paved section is concerned with the binder course paved on top. There is a 34 mm rut depth after 120 passes. For the unpaved section, it's very bad. It's about 100 mm rut depth after 120 passes. So you can see that in the photo there are some extensive cracking due to the tension of the pavement. So on the unpaved section, section B, this one we have a layer of geogrid with the same thickness of all this. If we compare the unpaved and the unpaved section, we totally the same section, but this one is with a layer of stabilization geogrid. You can see that the rutting that we measure is 17 mm as compared to 100 mm over here. The improvement is almost 5 times. Based on and if you look at these two, the performance is even better than the paved section. So with all these results, it convinced very well to our client that this is a good material to be used so that they can save some cost on the construction, and the most important part is that they can save a lot of time. So after that, we proceed and then I open this work for the construction vehicle for all the earthworks surrounding. For the unpaved section. So another one which I want to share with you is Sabah Bernam. Remember just now I talked to you on differential settlement. So how this one can tackle on the differential settlement. So in year 2002 is concerned, there's an excessive differential settlement on the new widened section of the road in relation to the existing road in Sabah Bernam, Serangoon. Okay. So it recorded about 150 mm differential settlement after 4 months on the completion of the widened section. Okay. Next. So we were called, my colleague, my ex-colleague, was called by JKR to actually go and access on this problem. And then he did a measurement. You can see that the paving is still quite new. He did a measurement over here and it recorded about 150 mm. This is I will use an old pavement. This is the old pavement and this is the new pavement.